Hello class. Today we are going to discuss a topic called vapor pressure. Now let us try to understand what does vapor pressure means. Say for example, if you take a liquid in a container, a volatile liquid, that means a liquid which can evaporate easily at room temperature or by heating. So what will happen if you have taken a half amount of the liquids and you are applying heat, some more heat, and the liquid is volatile? So what will happen after some time? The liquid molecules will start evaporating into the gaseous form, either by heating or by warming it, we can say. So what will happen? These are the liquid molecules. At the surface we have got the liquid molecules. So when you just a process called evaporation takes place, some of the liquid molecules will convert into the vapor form. Okay, now this process continues on until and unless the vapors that is produced over here will start condensing. That means it will start condensing, that means converting from gases to liquid form. So as the process increases, rate of evaporation decreases and rate of condensation increases. But at some stage of time, the rate of evaporation, that means the molecules transforming into gaseous form, and the rate of condensation, that means the molecules converting from gases to liquid form, becomes equal. At that time, the pressure that is exerted by the vapors or the gas on the liquid surface is called vapor pressure of the solution. So the pressure exerted by the vapors on the liquid surface at equilibrium is called vapor pressure of the solution or vapor pressure of that liquid. Now this is in case of when you have got a volatile solvent, that means when you have got a pure solvent, we can say. But in that solvent, if you have add some amount of solute, that means this solute, it becomes a solution. So in case of solution where we have got non-volatile solute, that means this solute does not convert into the vapor form, what will happen? The surface of the solution will be covered up by some non-volatile molecules. That means now over here the rate of evaporation will be less because some of the surfaces are covered by non-solid molecules. That means it will not convert into the vapor form. So what will happen? Less amount of vapor will be formed because some of the surfaces are blocked by the non-volatile solid. In that case, the vapor pressure or the vapor that will be produced over here will be less compared to the pure solvent. Okay, so in case of solution for a non-volatile solute, the vapor pressure is smaller than the vapor pressure of the pure solvent. That thing you have to keep in mind. Okay, so this is a general idea about the vapor pressure. Now we'll see a law related with it, and that is commonly known by a name known as Raoult's law. Okay, that is commonly known by a name known as Raoult's law. According to Raoult's law, he have stated, he have given two statements, one for volatile liquids or volatile solutes, another for non-volatile solids. Let us see for volatile liquids or volatile solutes. For a solution of, according to Raoult's law, for a solution containing volatile liquids, for a solution of volatile liquids, the vapor pressure of a component at a given temperature is equal to the product of mole fraction of that component in the solution and the vapor pressure P0 of that component in the pure state. P0 means vapor pressure of the pure solvent and P is the vapor pressure of the solution. So according to Raoult's law, it states that the vapor pressure of the solution, which is denoted by P, is given by the product of the mole fraction of that component into the vapor pressure of the pure solvent. Okay, now if the solution consists two volatile components A and B, then the vapor pressure of the resulting solution will be the sum total of the partial pressure. So if we have got two volatile components in the solution, then we can write it as vapor pressure of the partial pressure, vapor pressure of the solution will be equal to the vapor pressure of component A plus vapor pressure of component B, which is given by, we know that PA for first component, we can apply this formula, P naught into X. So P naught by A into XA plus P naught B into XB by putting this one. So this law is applicable only for completely miscible liquid. That means the liquids which gets easily mixed with each other. That is for volatile liquids. Now let us see for non-volatile solids. So as for discussed above, from Raoult's law we came to this equation from above, that is vapor pressure of the sum of the vapor pressure of the solution will be equal to the vapor pressure of the individual components, we can say. So as the solute is non-volatile, in this case, as the solute is non-volatile, its vapor pressure P A naught, that means if this is a solute, will be equal to 0, because non-volatile solute does not produce any vapor, so they will not have a vapor pressure, so it will be equal to 0. So by putting PA naught in this equation, it will be 0. So PS will be directly equal to this one, that is PB dot XB, and this is the solute and this is for the solvent, as we know. Now once again over here, XB is replaced by 1 minus XA. This comes from, as we know from the mole fraction definition, mole fraction of the solution is 1, unity. That comes from mole fraction of the solute plus mole fraction of the solvent is equal to 1. That means XA plus XB equals to 1. Therefore XB will be equal to 1 minus XA. So we have substitute over here. So when you just open the bracket, it will be PV naught minus PV naught by XA. Got it? Now after that, if you bring this to this side, it will become plus. It will be PV naught XA, and if you take it this to the side, it will be minus PV naught minus PS. Okay. Now if you find only XA, that is this the mole fraction of the solvent, will be PV naught minus PS by PV naught. So this is the vapor pressure of the pure solvent, and this is the vapor pressure of the solution. So from this equation, the Raoult's law have stated the statement for it. Now for solution containing non-volatile solute, the Raoult's law can be stated as the relative lowering of vapor pressure, the relative lowering of vapor pressure of the solution at a particular temperature is equal to the mole fraction of the solute, because Xa is the mole fraction of solute. Okay, so this is the another form of the Raoult's law statement. For a solution containing non-volatile solute, the Raoult's law can be stated as the relative lowering of vapor pressure of the solution at a particular temperature is equal to the mole fraction of the solute, from this expression. Because this is a relative lowering, because this is the vapor pressure of the pure solvent minus vapor pressure of the solution by vapor pressure of the pure solvent. This can be considered as relative lowering of vapor pressure. Later on, once again, we'll come across this expression when you do the colligative properties. Next, we need to know what is ideal solution. A solution is said to be ideal if it follows Raoult's law under all conditions of temperature and concentration. So a solution which obeys Raoult's law, the above law, at all condition and temperature, they are called as ideal solution. For ideal solution, there will be no change in volume on mixing the two components, that is del V mixing will be 0, and there will be no enthalpy change on mixing, that is del H mix will also be 0, as the components have similar structures and identical in intermolecular forces. A perfect ideal solution cannot be formed practically. Okay, it cannot be formed practically, but several solutions of very ideal solution can behave as ideal solution. Examples of ideal solution are N-hexane and N-heptane. The mixture of these two behaves as ideal solution. Benzene and toluene, ethyl bromide and ethyl chloride, chlorobenzene and bromobenzene. Okay, and now this is the graph for the ideal solution. over here, XA is the mole fraction of the solute, that is 1, and this is the solvent. So XA is 1 and XA is 0. And over here XB, solvent 1 and mole fraction of solid 0. Now over here, this vapor pressure of the pure solvent, and this is the vapor pressure of the pure solvent, and this is the solute. So the total vapor pressure P is equals to PA plus PB. Okay, and this is the just dotted line soon, because later on we will come across these the deviations, positive deviations and negative deviations of ideal behavior.